So good evening, everybody. Welcome to this evening's event, Exploring Pi. But I'll let our expert talk a lot more details about that. My name's Andrew, and I'm part of the outreach team at Liverpool John Moores University. So I'll kind of host any question and answers near the end of today. Just to let you know how today is going to be working. It's a live webinar, so you can't be seen, you can't be heard, so you can't accidentally, don't worry about your camera suddenly popping on or suddenly saying something. The way to kind of communicate will be via the Q&A function. So you should see that near the bottom or near the top, depending on how it looks on your device. So if you think of any questions throughout the time, pop it into the Q&A function. And then at the end, we'll have time to ask questions and we'll put them to Paolo. What we will just do as well, just as we're letting a few more people just kind of coming in, there has been a poll just launched, and that's just kind of asking whereabouts you are, what year you are, just so obviously in the Q&A session, we can kind of tailor some of those questions maybe to you guys. So we'll leave that on just for a few minutes. One of the things obviously at John Moores University we're quite proud of is that our maths department is really 5th in the country in the different league tables. And obviously, I'll let Paolo go into a lot more detail, but the department's very strong with its links with our students and hence putting them in for different awards and taking them on different field trips. One of the things obviously we would just say before we go into the proper talk is have a little look at the different departmental web pages. You can find actually really useful newsletters to see roughly what the department is up to. If you're interested in looking a bit more detail, you should be able to see a link for the Department of Mathematics and Computer Science in the chat there, and we'll put a link to the newsletter in a little bit later on. So if you've got any questions, obviously later on about John Moores specifically, please feel free to do them, or any questions about mathematics, because we know you would love to talk about mathematics. I got a sneak preview a couple of days ago on the session, so it's really, really interesting. And I will mention, we are continuing the way 2020 left off. So obviously you can see we're on our homes, we're not on campus. So we do apologize in advance if the doorbell goes, for example, during the session. If my 4-year-old son comes running in, I haven't asked Paolo, but if we've got a cat, for example, in case a cat walks on screen, because we know they like to steal the show. So just bear with us as we are at home, or because any tech issues do arise, but we'll get fixed pretty quickly and come back to you. So I've done far too much now, so I'll pass over to Paolo. I'll stop sharing my screen and hand over to Paolo for the main event.
Okay, hello, am I live? Let me know. Right, oh, hello everyone. My name is Paolo Lisboa. I'm the head of the department for mathematics at Liverpool John Moores University. Welcome to this webinar to celebrate International Mathematics Day. I'm hoping this will last only about 20 minutes. And in it, we're going to do a couple of examples of mathematics that relate to A-level mathematics, to AS level and A-level mathematics. The theme of today is how to bring order out of disorder with mathematics. And this is done in the way that mathematics can make sense of randomness. So you're going to look at some random experiments, i.e. experiments that involve random variables. And from them, we'll derive some very accurate predictions. One of them will be of pi. It's this ability to bring order out of disorder that makes mathematics so very useful in the real world. So to begin with, the thing that we're going to be looking at is called Buffon's needle experiment. And in this experiment, we use a piece of paper, something like this. Now, I don't know whether you can see this. Andrew, can you let me know?
Yeah, you can see that.
Okay, right. And this is a piece of paper. And in this piece of paper, we have a needle, right? And the idea is that this piece of paper has lines evenly spaced, and they are spaced by exactly twice the length of the needle. Okay? And you can have as many lines as you want, any size needle, any size piece of paper. And we're going to take this needle and throw it at a piece of paper randomly, so I don't look at where it's going. And we then check whether the needle is crossing the line or not crossing the line. And we keep doing this. And we keep doing this for a long, long, long time. You'll find a quicker way to do it in a moment, okay? Now, it turns out that the ratio of the number of times we throw a needle in, the number of needles, divided by the number of crossings is a very good estimate of this quantity pi. However, there are some problems doing this by hand. The first one is I'm human, I'm not a machine, and therefore my actions are not truly random. The second one is I'm going to lose count, because you want to do this thousands of times. In fact, during this lecture, we're going to do it 1,000,000 times, again and again and again, but not by hand, okay? So instead of this, what I'm going to do is to share the screen, and I'm going to use a computer, right? And in this computer, I'm going to share a figure. You should be able to see a figure which looks a bit like a piece of paper with lines. Can you see that, Andrew?
Yes, we can.
Okay, so this figure represents a piece of paper, and I'm going to throw a needle into it. Now you should be able to see a needle arriving in it. One needle by itself is not very helpful, so we throw another one, and another, and another, and another, and another, until we get to 10 to begin with. And you can see that now that we have 10 needles, the proportion of crosses is 3.333. That's because we have 10 needles and 3 of them cross. There's one at the top, and well, actually there are 3 at the bottom. One of these four crossing looking needles mustn't be properly crossing, probably the one at the top. So there are 3 that are crossing. Okay, so that gives an estimate of pi. Not a very good estimate, of course. So we're going to do it a bit more, but this time I got 50 needles, right? That's what 50 needles look like on a piece of paper. And the proportion of crosses divided into the number of needles is 3.125. And if you really wish, you can count. I don't recommend it. So we'll go again, and we'll do 100 needles. And of course, we're getting a proportional error, which is smaller and smaller and smaller, and then perhaps 1,000 needles. So that's what 1,000 needles look like. Something you always want to know, I'm sure. Okay, now 1,000 needles is a pretty big number, and the accuracy of estimating pi is still not very good. So it looks like this experiment is not all that's cracked up to be. So, well, let's do it for real. 1,000,000 times over. Well, actually, in order to spare your eyes, I've only plotted 5,000 needles, but actually I've done this 1,000,000 times. And if you look at the proportion of crosses into 1,000,000, the number of needles, you get 3.1425, which is okay, but it's not really brilliant. So what I'm going to do next is I'm going to do it, but do this 1,000,000 times, but instead of showing you the needles, I'm going to show you the estimate of this number, which is the ratio of the total number of needles divided by the number of crosses, okay? And you'll notice that what I'm showing you here is a logarithmic scale, okay? So being a logarithmic scale means that 1 corresponds to 10 needles, 2 to 100, 3 to 1,000, 4 to 10,000, 5 to 100,000, and you've guessed it's 6 to 1,000,000. So this number is converging like a limit onto an even number. So I've just done one experiment with 1,000,000 needles, okay? And just to make sure that the effect that I get is not totally chance-based, I'm going to do it again. So I get, I'm genuinely throwing random numbers. This experiment is running live. The code is running in real time. And I wrote the code, so I know exactly what it's doing. So I'm going to do it again and again and again and again, and keep doing this. I'm going to do it about a dozen times, okay? So what you notice is that after quite a large number of needles being thrown, somewhere around after about 100,000, the estimate of pi gets pretty good. And by the time you get to 1,000,000, the estimate of pi is really properly good. and the value of pi, the exact value of pi, is shown as a horizontal line. Okay, so what we've been able to show here is that by throwing needles onto a piece of paper, we are able to produce a very good estimate of pi. Okay, so that is the experiment. What is the theory? Okay, to show you the theory, I'm going to share another screen. And you should be able to see the header, Buffon's needle and other integrals. Can you see that, Andrew? Just
yeah, we can see that.
Okay, and this gentleman, very distinguished looking gentleman sitting there, is Comte de Buffon. He lived in the 18th century, as you can tell, and he was a French aristocrat with the title of Count, so he's Count of Buffon. His actual number was Georges Louis Leclerc, and is credited with having created this experiment we just did, which is considered to be the first proper simulation in mathematics, long before computers had been invented. Okay, so now let's look at the theory. So here's a picture of the piece of paper, and this is where I hope that my tablet's going to work. Okay, so I have in the middle of that piece of paper picked up on a needle, and yes, and I've indicated a triangle. I'm going to use that needle and that rectangle triangle, right, as a way to explain to you the theory, which involves some integrals of why Buffon's needle experiment works. But I agree with you, that triangle is tiny. So let's expand it, okay? So now you've expanded it, but you know what that triangle is, and that's the center of the needle. So because that's the center of the needle, notice that that's the center of the needle. The needle is of length 1. The gap between the lines is of length 2. So this bit of the needle is of length 1/2, right? Okay, so we have a rectangle triangle. So here's your 90-degree angle. So you can feel very comfortable in that home. Now, I'm sorry to go back again, but I want to show you one thing. The bit that's really interesting is this distance d here, because that is the side that determines whether or not this needle is going to cross the line. It's the ratio, if you want, between this distance here and the distance from the center of the needle to the line. That's going to determine whether the needle crosses the line or not. So promise I won't be going backwards and forwards anymore. So at this point, we're going to do some standard, in fact, GCSE maths, okay? So we know there's a relationship between d and theta, and that's to do with a basic trigonometry. Opposite, which is d, over hypotenuse is the sine. Okay, so that is the sine. Oh, wrong. That's the sine of theta. So that means that d, if you just put the sine of theta divided by 1, and then cross multiply, okay, what you get is that d is 1/2 times sine of theta. Okay, so as you guys can see, we can use this software as a whiteboard, even though we're delivering lectures by Zoom. Okay, so d is 1/2 sine theta. So the question then arises, when will this needle cross the line? And the answer is when the distance x from the center of the needle to the line, to the nearest line, is less than d. That means to say, therefore, when x is less than 1/2 sine theta. Okay, there's what it is. Okay, I think I need to improve my handwriting. So I'm going to make an effort on that just now, right? So what are the chances of the needle crossing the line? Well, to understand this, we need to do something. And what we need to do is to look at a bit of probability. First of all, we're going to throw a needle randomly. That means that the value of x is anywhere between 0 and y, 0 and 1, because if you remember, the lines are spaced by twice the length of the needle. The needle is of length 1. So if the lines are spaced twice the length of the needle, the nearest line will always, to the center of the needle, will always be only a maximum of a distance 1 away. This is the distance to the nearest line. And there's a basic principle of probability theory that says that if you have a probability theory, probability, and that probability is uniform, that is to say, it is constant in this range 0 to 1, then that probability, like any other, must have an area of 1. If you have a rectangle, which in this case will turn out to be a square, of side 1 with area of 1, it must have height 1 as well. So this probability is 1, which is nice because it disappears from our calculations. The next one for theta is more interesting because now we have that the angle theta is anywhere between 0 and pi by 2 in radians, because the needle can go anywhere between 0 and 90 degrees, which is pi by 2. This is again the angle to the nearest horizontal. So if it goes past that way, then you get an angle in the other direction, which is less than 90 degrees. Likewise, if it points downwards. So again, the area must be 1, and therefore this time the height must be the reciprocal of pi by 2, which is 2 by pi, okay? That's because we have that the requirement that 2 by pi times pi by 2, which is the area of the rectangle, is equal to 1. So that is 2 by pi, okay? So what is now the probability that this needle is going to cross that line? Well, that probability is going to be an integral of, I meant to say a summation if you want, a continuous summation over all the possible values of x and all the possible values of theta. So that's represented by this integral over here, where x goes from 0 to 1 and theta goes from 0 to 2 pi. So that looks a bit messy, okay? So let's write it out, okay? So when you write this out, what you then find is that the probability of crossing the line equals, and I'm going to continue writing my equals down here, equals the integral, which goes to begin with from theta equals 0 to pi by 2, sorry, 2 over pi, sorry, start again. The integral, the value of x goes to pi by 2, so, whoa. Go back again. Yeah, pi by 2, because the angles go from 0 to pi by 2, and x goes from 0 to 1. And now you have the probability of x, which is 1, and the probability of theta, which fortunately is just 2 by pi, right? Dx d theta, which looks still a little bit messy. And I realize now I'm making my numbers far too big, so I need to reduce. I'll increase the screen. Can you see all those numbers?
Yes, we can.
Okay. So now the probability of x. Right. There's one thing that I forgot to mention to you. And in fact, I rushed and make a small mistake. I forgot to mention to you, to remind you, that in order for the line to be crossed, x must be in the range of 0 to a half sine of theta. Because if x is, if the relationship between x and theta is such that x is bigger than that, then the needle is too far away from the line. And therefore, this integral over here, the integral that is over x, does not go from 0 to 1. It only goes from 0 to a half sine of theta, because that is the proportion of the time that the needle is going to cross the line. So that gives me the integral that we now need to do, okay? So the integral of x will give us a half sine of theta. This number 2 over pi multiplies it. And we still need to do the integral over theta, which goes from 0 to pi by 2. Right? So these two cancel out, and I get an integral of d theta of sine of theta multiplied by 1 over pi. So I'm going to get 1 over pi into, well, the integral of sine of theta is minus cos of theta. We know that from A level. Remember the minus sign. It's important. And if you go from 0 to pi by 2, well, the cosine of 90 degrees is, I'm showing you all of this. I'm writing all of this, and you can't see it. I don't understand why it is that my screen is expanding so much what I'm writing on my tablet. So it means that I'm going to have to go through it more slowly, and that's what I'm doing just now. So what I was writing was the integral from 0 to pi by 2 of the integral over x, which gives us a half sine of theta, times the value of 2 over pi that comes from there. So I'm now got the integral over here, and I got the 2 over pi. The 2's cancel out, and I get an integral from 0 to pi by 2 of 1 over pi, there it is, times sine of theta. The integral of sine theta is minus cosine. You need to remember the minus sign. And the cosine of pi by 2 is 0. So this is going to give us cosine of pi by 2 negative minus cosine of 0, which is 1. And the sum total is 1 over pi. So the probability of the needle crossing the line is 1 over pi, which is what's written over here. The number of crossings over the number of needles is 1 over pi. Therefore, if you keep track of the number of needles, divide by the number of crosses, you get pi. And that's exactly what we found. So what we have shown here through all of this calculation is that by throwing needles onto a piece of paper, rather like this, and if you throw enough of them, and count the number of crosses and count the number of needles, you will get the result, which is a very good approximation of pi, and we show that experimentally. And the calculation comes from using Pythagoras to give us the height of the opposite side, which is a measure of half and sine of theta, and making sure that the distance from the needle to the line is less than a half sine of theta, calculating the probabilities of the angle and of x being in the possible ranges, putting all of that into this integral to look at all the possibilities, and then carrying out that integral where you first integrate over x to give you, the integral is integrating a constant over x, so the value of the integral is just the value of this x at the top minus x at the bottom, which gives you half sine of theta, multiplied by 2 pi, that cancels out. And now you have to do the integral over theta, which is minus cos theta between 0 and pi by 2, and that gives you 1, gives you minus cos of pi by 2 plus cos of 0, which is 1. And presto, is your answer. Okay? So that shows that it is possible to carry out experiments where the trajectory of each individual object is random, but the aggregate properties are absolutely precisely predictable in sophisticated ways. Now, in showing that experiment, we ran with 1 million needles, which required a computer. And in fact, pi, of course, which is the number that we found, is related to circular objects like coins. So a natural thing to follow on from this is flipping of a coin or using a sphere, because if you want to flip a coin and get head or tail, you can instead use an experiment where you use a sphere going through an object where it bounces one side or the other. So you're going right or left, and that's equivalent statistically, if it's a fair ball, to a fair coin with a 50-50 chance of giving you heads or tails. Now, what I'm going to show you next is a very large number of experiments, which I'm going to do without a computer. So this time, I'm going to look at 12 steps, which are the beads bouncing on these pins, okay? And I got 3,000 beads at the bottom here. So we're going to do a sequence of 12 flips 3,000 times, and we'll see what we get. I think you can see we're getting a normal distribution. In fact, there's a reference line there. I'm going to do it again. There we go. Okay, so we have here a normal distribution, and because my my hand was slightly tilted, we get a slightly shifted normal distribution, but I'll do it one more time. I'll try and keep it really horizontal this time around. Okay, so we have a normal distribution. This time, in our normal distribution, we have not had to use a computer. So I'm going to share my screen one more time, and I'm going to go back to a note and look at this experiment in more detail. And it turns out that that involves an integral, but it involves an integral that is very hard to do, and we'll find a trick to do. It's an integral that everybody should know how to do, because it's an integral of something that you're going to use if you use mathematics pretty much all your life. And this is the fun bit, your teachers might not know how to do that integral, because quite a lot of people don't know how to do it. And it's not actually that difficult if you do it the right way. So that device I just showed you is called a Galton board. Okay, so that's called the Galton board. It's named after a scientist who's a little bit controversial. And if you want to find your own version of it on the web, if you browse Maths is Fun Galton board, okay, Maths is Fun Galton board, you'll find an app which is free from this website called Maths is Fun, even though you already knew that. And this website will give you this particular app that I just taken a snapshot of it, and it allows you to set the number of pins, set the probability of going left or right each pin, set the speed, and you can create as many bouncing balls as you want. Now, interestingly enough, these balls are going to just go right and left. They will not bounce like the ones that I was showing you earlier. So this is an exact and correct replication of the Toyn-Kosty experiment. This is actually not, it turns out. This is actually because the beads bounce off the pins. So this is actually a simulation of a gas. Okay, the bouncing of the beads on the pins simulates the speed of the molecules in a gas, and that is a reflection of the temperature of the gas. So a high temperature gas corresponds to beads going down very fast and bouncing a long way, and a low temperature gas corresponds to them coming down very slowly. And at close to zero temperature, you will get something very like this exact experiment that you see on the screen. Right? And for those of you who are doing the binomial distribution at school, well, what this is showing is that if you take a binomial distribution with many categories, it is well approximated by the normal distribution. Okay? Now, the normal distribution needs to have certain characteristics. It needs to be symmetrical about the mean. You can see here, it's roughly the same right and left if you have an unbiased coin or unbiased ball on a pin. It needs to extend to infinity, not in the case of binomial distributions, but for the real continuous distribution, it needs to extend to infinity. And it needs to have a given width that controls the standard deviation. It turns out that the normal distribution has got some amazingly optimal properties on something called entropies. They absolutely is a magical thing. And all of that was derived by this gentleman who was born in the 18th century and died in the 19th century, called Carl Friedrich Gauss. And that little beta looking symbol at the end is German for SS, Gauss. We normally write GSS. And the formula is a formula that you will have learned at school, I'm sure, and it's a formula that you learn at university. And in this formula, you have, let's not chop Gauss's head because that would not be very kind. So you have the mean value over there called mu, and because the function only depends on the distance between x and mu, it's symmetrical, because whether x is to the left or to the right of mu, it's the same difference when you square it. And it's got the width determined by sigma, and that is the correct formula for it. Okay, it's a major triumph for mathematics to show that that particular bell-shaped distribution has this exact formula. Okay, and that's something called the central limit theory that tells you that if you look at the mean value of any number of experiments, if there's a large enough number, the mean value will have that distribution, which is why even that gas simulation gives you this distribution very accurately. But there's a problem, and that's where the integral comes in. The problem is that, as we know, the area under this curve needs to be 1. So the area of fx, I'll try and stay on the window this time, when x goes from minus infinity to plus infinity, that has to be 1. And it isn't. Okay? So what we're going to do is we're going to say that fx is we're going to write it as equal to that same expression divided by some number a called the normalization constant. Okay, and I make sure that I've erased it approximate. And a is going to be the integral from minus infinity to plus infinity of the function f, or as it originally was. I've done it again, gone off the screen. I'll have to definitely stop that. Now, this function, which is the area of this bell-shaped curve, doesn't depend on whether the curve is located to the left or the right. It only depends on its shape. So you can position the mean of it any way you like. I'm going to position it at 0. So to do that, using my tablet's very easy. I just set this mu to 0. Okay. So now I have an integral that is fairly easy to do. Now, notice that this integral, I should have completed my integral by writing d of x, of course. I'm going to write it out now. Go on. Yeah, d of x. Now there's a problem. Notice that if you're trying to do that integral, you need to have to find something that differentiates to it. But if you differentiate this complex expression, the exponential of e to the minus sigma square of x squared over sigma square, and what I've done is I've set mu equal to 0. That's why it doesn't appear there. Differentiate, that's my tilde there, my dash. Then what you get is minus a half. When you differentiate, you first differentiate what's inside the argument. That's a chain rule. So you get minus a half times twice x over sigma square, which is this. And because you're differentiating the exponential as well, the exponential gives back itself. So what you get is minus x over sigma square, it minus a half times x squared over sigma square. Right. And the problem you now have is this little character, this x. Now, it's a big problem because it's missing from the top, from the integrand. And unless you have x in the integrand, you cannot do the integral. So it's essentially an impossible integral that we're going to try and do. And in doing it, we're going to use this property. Okay? So we now have an impossible integral. So what we're going to do now is try and do that impossible integral. How are we going to do it? Well, we're going to do something that on the face of it looks a little bit ridiculous. We're going to square it. So remember that a is that integral, right? So I'm going to square it. So I'm going to say, well, a squared is this integral from minus infinity to infinity e to the minus, and I'm going to write it like this, just for the sake, for brevity, right? To begin with, and I'm going to square it. But when I square it, I'm going to use a different variable. I'm going to call it y, and you'll see why in a moment if you don't mind the pun. Okay. Now, instead of having one difficult integral, I've got two difficult integrals multiplied together. So why on earth would I want to do that? Well, there's a really good reason why you want to do that. And that reason is that now I'm no longer doing an integral over the real line. I'm doing it over a plane. Okay, so how does that help you? I hear you ask. Well, you should be asking. Well, it helps you because on a plane, I can use a different set of coordinates, right? So on this plane, I can use not Cartesian coordinates after Descartes, which are the ones x and y, these things. I can use polar coordinates. In polar coordinates, I determine a point not by the value of x and y, as we normally would do, but by the distance from the center and by the angle to the horizontal. Okay? Now that's quite handy because there's this nifty trick I'm going to show you now. I'm going to do it in green, which is the following. The element of integration in an area, dx, dy, which corresponds to a little bit of space that we're going to integrate over, now is determined by polar coordinates. So instead of being rectangular, it looks like an arc. Okay? And the area of this rectangle is dx dy, because dx is, if you want, dx is the size of the bottom of that area, and dy is the size of its height. But in the case of the polar coordinates, it's much more fun than that because the area is given by the delta r, which is the increase in radius, obvious, but that's the bit now that's going to save us, this bit on the side here, because that is an arc. And if you remember from your geometry, the size of an arc, a distance r away from the center, is r d theta. It's not just d theta, it's r d theta. Okay, so now that's going to be proper handy because now I can rewrite my integral, and my integral, which involved dx and dy, now is written as the a square is now the integral over r from 0 to infinity, because the radius from a plane, if you want to cover the whole plane, you go from 0 to infinity, and the integral over theta going from 0 to 2 pi, because you have your radius going from 0 to infinity over the whole of the plane. And the argument is now e to the minus x squared plus y squared over twice sigma squared. And I'm going to show you why that is so handy, because you know from Pythagoras that x squared plus y squared is equal to r squared. This might even look like an r if I'm a little bit careful, which means that that integral can now be written in the magical form, which is 0 to infinity dr, 0 to 2 pi d theta, e to the minus r squared over twice sigma squared, with one change to my equation. And that change is that, if you remember, the element of area is r d theta, not just d theta, okay? Which means that the element of the little rectangle dependent on theta is now r d theta, and this has got an r d theta over here, and that's what's going to help us because it's going to provide that value that was missing earlier on. So to show how this works, so coming back to this integral, a squared is therefore going to be, well, The first thing is I can do the theta integral because there's no dependence on theta anywhere. None of this depends on theta. It only depends on r. So the theta integral just gives us 2 pi. And the r integral gives us the integral from 0 to infinity of r, which is that r over here, e to the minus r squared over twice sigma squared dr. Okay, and that's very handy because this is the integral that we can do because you have this drop down term r that allows us to integrate the e to the minus r squared. Okay, and when you do this, what you get is your 2 pi, and it turns out that the integral of all of that in the integrand is e to the minus r squared over twice sigma squared. I'm going to go back up and show you. So I'm going to go back up and show you why that is. It's because of that property that the derivative of e to the minus x squared over twice sigma squared is minus x all of that, minus x over sigma squared all of that. Therefore, the integral of e to the minus half x squared sigma squared multiplied by x, which is what we now have, but with an r instead of an x. So the integral of x e to the minus all of that is equal to minus sigma squared times that lot. So that's what we're going to write now. Put the minus sigma squared there. And it's done between 0 and pi by 2, 0 and 2 pi, because that was the integral that we're doing. Sorry, 0 and infinity, because that is the integral of r. Okay, and if you take this expression and work it out, you get 2 pi sigma squared. Then you have, I'm going to put the minus sign inside the integral. So I'm going to have minus e to the minus r squared over twice sigma squared. When r is infinity, it gives you infinity squared, and then minus e to the minus 0 squared over twice sigma squared. And this is infinity. Okay, and e to the minus infinity just gives you 0, because the exponential of a negative very large number is 0. These two signs add up to a minus, because we know that 2 is up to a plus, because 2 minuses make a plus. We know that any power of 0 is 1, so e to the 0, e to the minus 0 square over something, well, e to the 0 is 1, so that gives you 1. And therefore, the total integral just gives you twice pi sigma square, which means that the value of a is sigma root of 2 pi, which is the square root of 2 pi sigma square, with the consequence that the value of the function, when you put the value of a back into the denominator, is as written on the screen. Okay, so just to recap very briefly, we started with an expression that needed normalizing. The normalization is the integral of the top, because when you integrate f with a in place, you integrate the top and you divide by a, but a is the same as the integral of the top, so you get 1. So you get the requirement for the probability distribution, the probability mass function called f, to integrate to 1. So to do that, you need to calculate this impossible integral, where you can set mu to 0 as you wish. But you realize that when you want to integrate an exponential, you have the problem that the derivative of an exponential with x squared in it is going to require a value of x multiplying the exponential. And we haven't got that value of x in the integral above. So we resort to a trick. We square the integral by having it multiplied by itself in the direction x and in the direction of y. That enables us to change from Cartesian coordinates to polar coordinates. And in polar coordinates, we know that the area element corresponding to theta has a factor of r. That's because this arc element here has a length that depends on how far you are from the origin. So the area element is the change in r multiplied by r times the change in theta. And that comes to our salvation here, because x squared and y squared is the length of the radius square. Therefore, that integral can be written in this form, which is an integral over r and over theta. The theta integral is trivial because there's no dependence on theta anywhere, right? So we end up with an integral over r, which has the element of r multiplying e to the minus r squared that we needed in order to be able to do it. And when we do it, we get just the exponential. That's because the derivative of this exponential is the exponential times the derivative of the argument by the chain rule. And that gives you our twice r with a minus sign, which is over here. And the value of 2 cancels out with that value of 2, and you put the sigma to compensate. So all of this, believe me, adds up correctly. This integral has now been done. The impossible integral, when you square it, has been turned into a possible integral through this trick of converting from Cartesian xy coordinates to polar r theta coordinates. So the integral corresponds now to this exponential term that you must find between the limits of 0 and infinity, because that's the limits for the radius. At infinity, you have e to the minus infinity, and e to the minus infinity is 0. So that drops down. So that term disappears because it becomes 0. This term at the lower limit is e to the minus 0, and 0, up anything to the power of 0 is 1. So that gives you 1. And therefore, your whole integral just becomes 2 pi sigma square. The square root of that, which is a, because remember, this is the calculation of a squared because you got the integral twice over. So that gives you a equals to the square root of 2 pi sigma square, which is the square root of 2 pi times, well, the square root of sigma square is sigma, so I pull it out to avoid confusion. And we write it out like this. So this is the formula that you will see in every statistics book, in many mathematics books. It's a formula that you'll be using in the normal distribution at school, you'll be using at university, you'll be using it if you work as a mathematician or as a statistician for most of your lives, but you now be able to say to anybody, including your teachers, I know how to calculate that number. And I bet you quite a lot of people don't. So today we looked at 2 experiments, both of which involved random things. In one case, we had random needles going on a piece of paper, and from the position of those random needles and whether they crossed the line, we could estimate pi. And in the other one, we had thousands of beads coming down over a load of pins to replicate the normal distribution, which has a complex formula that you now know, with an even more complex normalization constant that you now know how to find. So that is the end of the lecture. In it, what we've seen is the power of mathematics in turning randomness into order. And it also illustrates something that is typical of what we do in Liverpool John Moores University in the mathematics department, namely that we focus on real-world applications and the theory that has practical value. And you do that by using rigorous mathematics, combining calculus with statistics where is appropriate, and using computer software also, because that's what you're going to use in the real world. And that code that I showed you to calculate the experiments with needles is written exactly in the software package that we teach our first years, and then they use it through the second and third year of study as well. I hope you enjoyed the lecture, and if you're planning to study mathematics as a subject, it's one of the subjects that's got the most possible career paths, so wherever you study it, it's a pretty good choice. And if you decide to come to us, leave a better choice. So thank you. Over to you, Andrew.
Thank you very much for both of those, Paolo. So now we've got time for questions, if anybody would like to ask them. Mentioned earlier, if you use the Q&A function, that'll be the way we'll do it. So it's either going to be at the top or the bottom of your screen, depending on where it is. Type your questions in, we'll answer them live, so they will be anonymized, so don't worry, even if you think it's a silly question. If you relating to, obviously, the talk that you've just heard, or just general questions about mathematics, or if it's about entry requirements, for example, we'd happily be able to talk to you about them, or other things that might be included, for example, on a maths course. If you're wondering why, for example, I'm looking at this way, I'm not ignoring you guys here. It's just I've got the Q&As up on my second screen. So don't be thinking, oh, they're ignoring us there. What's going on? So we'll leave it open for a couple of minutes. If not, thank you very much for your time this evening. If you don't have any questions, certainly I know I'll be having pie of a different type. I'll be going for, that will be what my dinner is tonight. I had to get a mathematical kind of joke in there if I could, just so the head of admissions would be going, oh my God, he's done it again. So we've got a question. Why does the needles experiment relate to pi? Is it coincidence?
Well, that's a very good question. In fact, this number pi is related to the circle. And the reason why it relates to pi is because the position of the needle and whether or not it crosses the line depends on the orientation of the needle. So that's where the circle comes in. So it has to do with the fact that your needle orientation means that the tip of the needle spans a circle. And that's where you end up getting your pi from. In fact, there's a famous story to do with pi and to do with the normal distribution. You'll notice, and that's one of the things which I should have mentioned, so thank you for the question. You'll notice that the normalization constant that we just calculated is 1 over sigma square root of 2 pi. Now, there are many famous experiments in statistics to do with the normal distribution. And one of them was actually done in a prison, believe it or not, where someone looked at the heights of prisoners. Why a prison? Because they had access to a population that couldn't escape, and they could go and measure all their heights. So they could get loads of heights, and they found the normal distribution. And they showed that the normal distribution fitted very well with that expression, including the normalization constant of pi. And a famous social scientist said, I cannot believe that the height of people has anything to do with the diameter of a circle, or rather the perimeter of a circle. Well, the reality is that it does. So in the case of the needle experiment, is to do with the orientation of the needle, but it is also true that pi finds its way into deep statistics precisely because of its presence in that normalization constant. And so it could well be that that little trick that we played of going from Cartesian to polar coordinates, which means instead of using xy, we use r and theta, which puts the theta in, which is where the pi comes in, that little trick actually contains within it the gem of something much more deep and fundamental. And that is the reason why pi gets into the equation for the normal distribution, which is everywhere in statistics. The central limit theory says that anything you measure, if you measure it often enough, will have a mean value determined by the normal distribution. A long answer to a short question. Are there any other questions?
Yes, we've got another person has just asked, so how would the distribution change if the width and the length of the needle were not 1/1/2?
Yeah, okay, that's another good question.
You know what that means.
Yes, I know what that means, and it's a good question again. Yeah, so what we did was to use a needle that we called of length 1 by definition. We defined the length of the needle to be length 1, and then a piece of paper as lines that are spaced by exactly twice the amount. If you have lines spaced by a different amount, then that equation that says that the needle will cross when x is less than a half sine of theta will change depending on the ratio of the spacing of the lines to the length of the needle. And therefore, what you'll find is that you'll get something that depends on pi, but it won't be exactly pi. It might be a ratio of lengths times pi or something else. So the theory still works, but you'll not have these neat cancellations of 1s and 2s. You'll have other numbers that fit into there. So you'll get something multiplied by pi. So if you prepare to do it and do the experiment and then measure what you get, you'll find the theory still works. But for the sake of simplicity, if you use lines separated by twice the length of the needle, then you know you get exactly pi. And that makes the experiment just neater. But the theory always works. Another question? There's another question I just saw.
Yes, sorry, but my computer just went.
That's okay. That's okay. What grades will I need to study maths at JMU? The standard grades is 3 Cs, but we are a little flexible on that. And therefore, if you feel, and the only major requirement, the only requirement that we will not be flexible on is passing mathematics A level, because if you want to study A level at university, you need to show that you can pass your A level in mathematics. And so you expect a C in that. But if you don't quite make a C in some other subjects, then talk to us and we'll talk to you, and then might still be a possibility. But the standard offer is 3 Cs. Now, some universities have a higher offer than that. And so you might argue, why 3 Cs? Well, because there's something very special about John Moores University. And it is this: we have a group of staff who do a lot of research, but are passionate about teaching. And we provide excellent levels of student support. So we have students who come to us with grades that perhaps wouldn't get them into other universities, for good reason, because they probably would not pass a degree in mathematics in another university, because they wouldn't be getting the level of student support they'll get with us, but they will pass with us. One of the things that we should tell you is that if we let you in, then we know you're capable of passing. And our pass rate is way over 90%. And in fact, our employability rate is also over 90%.
Cheers, Paul. And if anybody does have any questions about qualifications, I've just put into the chat there the FET admissions email. So if you're not too sure about something, do drop us an email about it. It's 112 UCAS points is the equivalent as well. So if you were doing an A-level, a couple of different combinations, as long as you get those points as well, that should be fine. And if you've got questions about your application form, do feel free to let us know about that as well.
Indeed. And if you are an applicant, so if you already applied to us and you want to find out more about the detail of what we teach, we have an applicant day tomorrow morning. And I'm sure if you search for it, you'll be able to find it. And even if you haven't registered, you're still in time to register.
Yeah. So if you're an applicant, come along for tomorrow, because I know probably you were saying you're there tomorrow, so you can go and ask you more questions about that. Or I know we've got quite a few people who are looking at 2022 entry as well. So we will be doing open days on the 18th and 19th of June, if I do remember rightly. So you can obviously register yourself for them. And potentially, hopefully, we're all fingers crossed, we will be running on-campus events as well. Hopefully, at least from September, if we can maybe do it a bit early, we will do, if it's safe for government requirements. It looks like that's pretty much it there.
We've got an hour, which is more than I intended. So you guys done really well to stay in for an hour. So thank you very much for your attention. As I said earlier, good luck with your studies, whatever subject you study. But if you study mathematics, we need you guys as many. Mathematics is the engine of the modern world. So we need you, and you'll get jobs.
I think one of the great things to kind of complement, I think what you said as well, part of it earlier, was the amount of different career pathways that, mathematics can lead to, and a lot of different careers that people might not even associate maybe comes from a mathematics background. And obviously that's the type of questions to be asking at those applicant and open days of, where can this lead me to? So yeah, do feel free to look into that. But yes, thank you very much for yourself, Paolo, for that really interesting, both experiments tonight. And thank you everybody who came in. It was great to see we had representation from across the UK. So hopefully the weather stays nice for you over this weekend. Stay safe, and it won't be too long now. Hopefully we can say that we will be able to see you in person in the not too distant future. Have a lovely evening, have a lovely weekend, and we'll see you soon.
Bye-bye.